Hey guys, this is Marco with Students Teach Orgo. Today we're going to just be talking about polymerization really quick, so let's hop straight into it. First of all, what are polymers? Basically put, polymers are very large molecules consisting of repeating units called monomers. So here, in this example, this is a polymer called polyvinyl alcohol, and if you can imagine at these ends here, it's kind of just this pattern repeating over and over again. It's OH and then separated by two carbons and then another OH. So our repeating unit here, our monomer here, that this polymer consists of is this kind of 2-carbon, 1-alcohol unit, right? So we have an alcohol and 2 carbons, and then that's bound to another alcohol and 2 carbons, and then that's bound to another alcohol and 2 carbons. So that's our repeating unit. Now, just instead of having to write out a million of these monomers over and over again, we have this shorthand notation where we just put brackets around the constituent monomer, like so, and then the subscript n here outside of the brackets denotes that there are n monomers in the polymer chain, where n is just some integer. So polymers are very useful. They have a lot of industrial, research, biological, and everyday applications, and many more. So now we're just going to get into some ways of synthesizing polymers from their constituent monomers. So first up is amide synthesis. Amide polymers can be made by a dehydration synthesis of some sort of free amine and carboxylic acid group. So you'll see here on the left side, right, we have these two identical, these are actually amino acids, and you'll notice that this carbon here, the carboxylic acid carbon, it's fairly positive, and each amino acid has this free amine group on the end, and the nitrogen has a lone pair, so it can act as a nucleophile. So the lone pair on the nitrogen will attack the carboxylic acid carbon and force one of the electron pairs in this double bond up onto the oxygen, and then that gives us this sort of tetrahedral, I guess, intermediate. And then we can do a proton transfer to create a good leaving group, a water leaving group, and then have that leave and reform our double bond with this oxygen. And what we get is this amide group right here. And this amide group is part of the backbone of the polymer. So like the really long chain of atoms that stretch the length of the polymer becomes part of the backbone. And again, in our shorthand notation, we have sort of these brackets with the subscript n, just denoting that this subunit repeats n number of times. So again, for amide synthesis, we start with this ester carboxylic acid and a free amine, and the free amine attacks the carboxylic acid to create an amide, and the amide becomes part of the backbone. Now, very similar to amides are caprolactams, which are basically amides, but they are cyclic amides. And the mechanism here is a little bit different. Because we're starting with a ring, we have to first open the ring, and then we can perpetuate the reaction and create our very long polymer. So looking here on the left, right, we start with our caprolactam, this cyclic amide, and you can see the amide right here with this double bonded O and the adjacent nitrogen. For caprolactam synthesis, we do need a catalyst, which is just this ammonium ion here. And using the ammonium ion, we will protonate the amide oxygen and make this carbon here just a tad more partially positive. And then when we do make it more partially positive, this free amine that we have in solution can attack the carbon now. And then similar to the last mechanism, it forces the double bond up. And so we're left with this intermediate here. Again, we can do a proton transfer and convert this part, this nitrogen here, which was part of the initial amide, to a good leaving group. And then we can form the double bond again at the O, kick off the NH2 plus from this carbon, and end up with a free amine. And you'll notice that now we have opened the ring and it's linear. And then finally, we can use the NH3 now, the ammonia we have in solution that we got from deprotonating the catalyst, to abstract the hydrogen from, or the proton from this oxygen here, and then that replenishes our catalyst. So now that we have this molecule, this amide here with the free amine at the end, you'll notice that if we have this step again in solution with this new product, the free amine here will attack that carbon instead of the free amine at the beginning. And so that's what perpetuates the polymerization reaction. That's where the chain reaction comes into play. So after we attack here, and then this ring will open as well, then we'll have two of these linear structures together, and then that will repeat indefinitely, and that gives us our polyamide, which in shorthand notation we have written out here. So again, for caprolactam synthesis, we're using the caprolactam first, then of course the catalyst, and then finally the free amine to just initiate the reaction by doing the first ring opening step for us. Lactones can also be used to make polyesters. Lactone is a cyclic ester, and this mechanism is pretty similar to the caprolactam mechanism. It's late, and just without all of the protonation steps, because what we're using to initiate the reaction, this methoxide here, or alkoxide ion in general, is sufficiently nucleophilic without having to protonate anything to attack. So this will attack the ester carbon right here, force one of the electron pairs of the double bond up. We're left with this intermediate, and now we can reform our double bond and kick off the ester oxygen, or the ester bridging oxygen, I guess. And we're left with this now linear intermediate, and just like the last mechanism, this free end here, the O- can attack the next lactone to be added to the chain, and then we're left with this. And again, at this step, the arrows are just going to be the same here, and we're left with two of those linear units, and we can just continue that indefinitely, and then we get our polyester, which looks like so. So for this mechanism, we are starting with an ester, or a cyclic ester, a lactone, but this also works for just regular esters, and also an alcohol or alkoxide in order to initiate the reaction. Okay, and then finally, the last mechanism that we're going to talk about is radical polymerization. So we can use alkene-derived radicals to make polymers via a chain reaction mechanism. And then so this has three main reaction steps. First is the initiation step, which is first creating the radical. So you can see that here in this first step. We have some alkene. Here we have propylene, and we react it with either hydrogen peroxide or this AIBN reagent, and then that will form the most stable radical. So that radical is with the radical electron on this middle carbon here. And then we have the chain reaction steps, which you take the radical electron from that middle carbon, and then a double bond on any adjacent or nearby alkene. One of those electrons from the double bond will form a single bond with the radical, and then the other electron from that double bond will move over to the adjacent carbon and become a new radical itself. So you can see that here in this middle step, the radical that we made in the first step, in the initiation step, and one of the electrons from the double bond form a new bond, right? So this bond right here, and the other electron from that double bond becomes a new radical right here on the adjacent carbon. And then that sort of just repeats for as many times as we have reactant and solution, and so what we end up with is our polymer, which will look something like so. Again, so for polypropylene, we have this 3-carbon repeating unit, and it's connected here and here. Now, the last step, the termination step, it usually occurs either when the reaction reacts, when the radical, this radical here, reacts with some other growing radical chain, and then the two radicals will form a single bond, or it will react with an impurity, or you'll just run out of reactant in solution. We'll get into some practice problems now. So go ahead, you can try this one for yourself, and pause the video, and when you're ready you can come back. Okay, so Kevlar is a polymer used in bulletproof vests. Given its structure, draw the structure of its constituent monomers. So this requires a little bit of interpreting. So looking at this first, we see that in like the very long backbone here, we have these amide groups throughout. So that should tell you that this is formed probably by amide polymerization. And if you'll recall, for amide polymerization, we need an amine and we need a carboxylic acid. So we can see that we can get amines if we like cut these bonds right here, these amide bonds between the C and the N, right there. You'll see that we can kind of get like a free amine structure looking thing here. And then if we go to the other side of where we cut, you'll see that we have this almost carboxylic acid looking thing there. And all we need to add is the OH to each of those carboxylic acid carbons to complete that, right? And so that is our answer. Those are the two monomers that make up this polymer. So again, this first double carboxylic acid thing can be attacked by either of these amines here, and they'll be attacked with the carboxylic acid carbon. After the proton transfer, then this OH group will become OH2 plus and become a good leaving group, and then we're just left with an amide, as you see here. All right, number 2. Okay, so for this one, kind of similar to the last problem, just looking at this, you'll see that in the polymer backbone, so right here, we have these ester groups, and so that should tell you that this is formed by polyester synthesis. And if you remember from the lactone slide, we said that for polyesters in general, you basically need a carboxylic acid and an alcohol. And kind of doing what we did in the last slide, where we're cutting these bonds right here between this, like the ketone part of the carboxylic, or the ester, right? You can see that we have this structure right here. So that's ethylene glycol. And then if we add the OH back to this carbon after we cut here, we get the same reaction that we had on the previous slide. It's this benzene ring with 2 carboxylic acid groups in the para position. And so that is the answer for this problem. So again, if we attack this carboxylic acid group, this carbon here, with ethylene glycol, this group will attack here. After a proton transfer, this will become a good leaving group and come off, and then what we're left with is just this repeating. All right, problem 3. Okay, so for this one, you'll notice that here we have an ester, or this like diester kind of thing, and then this diol. So that should signal to you that this is going to be a polyester. So kind of like on the last slide, these alcohol groups will attack the ester carbons here. After a proton transfer, this group right here, this ethoxide, eventually turning into ethanol group, will become a good leaving group. And so what we end up with is this kind of part down to this kind of part. And so just looking at the mechanism, one thing I should point out is for the diol, you can deprotonate the alcohols, and then they'll still be nucleophilic and nucleophilic enough to attack the ester carbons here. Either way, I guess it's okay. But so you take the alkoxide here, attack the ester carbon, and that will kick up one of the electron pairs in the double bond to this oxygen, and so you're left with this intermediate, and then now you can reform that double bond and kick off this what will now become an ethoxide group, leaving group, and so we get this, and then that just repeats. Now this can react on the other side, so up here, and then you will get this unit right here on this side as well, and then that will just repeat for as long as you perform the reaction. And so our final answer is something that looks like this. All right, problem 4. Okay, so looking at this, this is a caprolactam synthesis. We do have our caprolactam molecule here, and we have a free amine and our catalyst. So going into the mechanism really quick, the first step is, of course, the protonation. So we'll protonate using the catalyst. After protonation, we can attack with this free amine here, and that will form this intermediate. After we form this, we get a proton transfer, so this NH will abstract, or this N, I should say, will abstract a proton from this N. That will convert it to a good leaving group. We could reform the double bond. And after we do so, we open the ring in the process, and then finally we can take that H off using our base, and that gives us this linear structure, and then that will just, again, now we have this free amine end, and then that can react up here with this intermediate. And then so the process just repeats, and what we end up with is something that looks like this. All right, problem 5. Okay, so looking at this, we have our ester here, a lactone, cyclic ester, right? And this alkoxide. So going into the mechanism, the alkoxide will attack the lactone carbon, that ester carbon, move one of the double bonds up. Now we can reform the double bond and kick off this this O here to open the ring. So we'll go ahead and open the ring, and now this free O- end can go back and react here with the initial reactant that we had, and just subsequently open rings from then on, and what we end up with is this sort of molecule right here. Okay, problem 6. So looking at the structure here, you'll see that we have kind of two repeating groups, right? So this first one here, the styrene group, first repeats n number of times, and then that's bound to this poly 2-vinylpyridine or 2-vinylpyridine group that repeats m number of times. So for the styrene, you'll notice that we kind of have these two carbons and then some sort of group, right? In our case, it's this benzene ring, and then after that, it will repeat again. So we'll get two carbons and then a group, and then two carbons and then a group. And so when you have this kind of two carbons and then a group sort of thing, that should signal to you that this is a radical polymerization mechanism, most likely, right? So this right here, the bond between those two carbons, initially was an alkene, right? And then after converting it to a radical, then it will react with other alkenes. So that will form like the two carbon and then a group, and then two carbon, then a group. And that's the same sort of deal here for the 2-vinylpyridine. We have these two carbons, and then the pyridine group, and then that just repeats. So the constituent monomers look something like this. And then you don't have to stay for this, you can leave if you want now, but for those of you who are interested, the mechanism kind of looks something like this. So starting with the styrene first, the styrene, we can react it with some sort of initiator, so just hydrogen peroxide because it's easy. That will form the most stable radical. And then now when we bring that radical near another styrene group, it forms a bond, single bond with one of the electrons in the alkene, and then the other electron in the alkene becomes a new radical, as we see here. So that will repeat n number of times. And then for the vinylpyridine, the 2-vinylpyridine, it's the exact same mechanism, where instead of styrene, we just replace this carbon here with an N to get our pyridine group. And so what we end up with is this. And then for the termination step, like I alluded to on the radical polymerization slide earlier, one of the ways that the reaction can end is if two growing radical chains react with one another. And then that's exactly what happens here. So we have this radical here reacts with this radical here, and they each have one electron. 1 + 1 is 2, and then the two electrons will make a single bond. as we have in this molecule here.